Okay, so last time, continuing from last time, so one of the things we showed was that if let A be an n by n matrix with entries from the field F, the columns of A form a basis Fn if and only if A is invertible. And how did we show that? We showed it through linear independence. We essentially argued that uh, for Ax equals to 0, consider the equation Ax equals to 0, and let's consider uh, these guys as, so there's an intimate connection between linear independence and having these guys having a trivial solution. So this equation has a trivial solution if the columns of A are linearly independent, and we also know that that will happen if and only if A is an invertible matrix. So that's a connection between linear independence and being an invertible matrix. Also, we know that we have n of these guys. Uh, so not only they are independent, they are n in number, and since the dimension of our vector space is n, these guys indeed form a basis. So we have a set of linearly independent vectors n, and they form a basis for an n-dimensional vector space. Okay, then we dealt with we started dealing with the notion of these abstract vector spaces. Till now, we were dealing with these column vectors, but nothing stops it from defining uh, and working in basis for general vector spaces. We consider an ordered set of vectors. Now, they are not column vectors, they are just some n objects, but we can still define a scalar product, which is namely v1 x1 plus v2 x2 so on vn xn. So that gives you a linear combination, and that can be regarded as and any vector can be, let's say any vector can be expressed through this sort of a linear combination where these guys are the coordinates and this is my basis. uh, I can also write down, I have this guy and I have some matrix over here that gives me a new set of vectors where each of the wj, some wj over here, is obtained from multiplication of these elements and the jth column out here. So wj is nothing but v1 a1j plus v2 a2j, so on and so forth. Okay, so that would be your a1j, a2j, so on and so forth. So as an example, I have v1, v2, and I can have some columns, and that gives me vectors. Okay, so why bother about this? I think it is in general important to consider vector spaces not only as column vectors but in an abstract notion, but they are equivalent as we see now. So consider this, which we can show every n-dimensional vector space is isomorphic to another n-dimensional, any other n-dimensional vector space. By that I mean they have the same structure. So that means that there is a bijective, which is one-to-one and onto mapping between these guys, the two vector spaces. This is a map such that the vector addition is taken over, whether I add the vectors and put the map, or I put the map and then add the vectors, and also the scalar multiplication. So this preserves the structure of the structure of vector space. So why this is useful for us? Well, consider the vector space of column vectors and our abstract vector space. The coordinates here get transformed through this bijective mapping into, so this mapping sending this to bx. So why is this a bijective map, or why is this an isomorphism? Well, it is surjective in the sense that B spans the vector space V. So it is true that every vector V in V would have a pre-image in f of n, and it is injective. That's because B, the basis, using the basis we have a unique way of mapping each of the coordinates x into this guy. So this is unique, and each of these guys has a pre-image, so it is an onto mapping as well. So what does this show? This shows that Fn is isomorphic to every V. So all we need to know the structure of Fn, or set of column vectors. That's why linear algebra essentially is a study of matrices and column vectors. So all we need to know is the structure of of Fn to know about V. Okay, lastly we see the problem of the change of basis. So essentially, let's say we have two bases. I denote this by, this is B prime, and I have another basis Vn. Now, how do I go from one of them to the other? Well, the idea is that let me define a matrix which does the job. This matrix P takes this guys to the another basis B. Why would such a matrix exist? Well, since B prime is a basis and B is also a basis, every vector here can be represented as a linear combination of these guys. Hence, I have a matrix over here. So essentially, that's what I'm saying. Each of Vj over here is just the linear combination of one of the columns of these guys. Similarly, what we did. So this is essentially the change of basis. And well, the change of basis in invertible, how do I see that? Change of basis is invertible. I can do exactly the same thing. So I had B prime P was equals to B. I can have B some matrix P prime equals to B prime. Well, that's just interchanging. So what do I get? I get B, I plug the value of one into the other, and what do I get? I get B P prime P is B again. So now I have B P prime P is equals to B, which gives me the same matrix again. I can argue that this is an identity matrix. And how do I argue that? Just think about it for a second. Well, the idea is that B is a basis, and elements are uniquely expressed in the spaces. So we should be able to express every vector uniquely by this basis, and we already know one unique mapping over here, which is v1 gets mapped to v1, v2 gets mapped to v2, so on and so forth. So I have v1, v2, vn. I plug in the identity matrix and I get v1, v2, vn back. So this was essentially the change of basis I was dealing with. So b prime x prime, yeah. So now what is left? Now how do I know the coordinates, the relationship between coordinates x prime representing the same vector, some same vector in two bases? So these represent the same vector bx and b prime x prime. What's the relation between these two guys? Well, I know that b prime x prime, plugging in the value of b, is nothing but b prime p x. Here I'm just plugging b prime p as b. So what do I get? Since this is an invertible matrix, I get x prime is equals to px. So it's the same matrix P, which not only tells me the relationship between the bases, but also tells me relationship between the coordinates. Okay, thank you.